So let's discuss complex functions now. Moving on to the higher levels. We have seen the basics just before this. So now moving on to complex functions. Okay, so let me write down the definition first. If for each value of z, which is a complex variable, in a given region R, okay, so for each value of z, complex variable z, if we have one or more values of w, which is say can be expressed in u plus iy, then w is said to be a complex function of z. So for each value, for each value of z, if we have one or more values of w, then w is called complex function of z, and we write w to be f of z, basically u plus iy, where u and v are functions of xy. This is how we write. Well, this is like just a function of a real number, like log x is log of a real number, and similarly like that you can have log z. Okay, so we'll see all that. Similarly exponential, so we'll see all those. Okay, examples of basic functions. Okay, so let's see one of the examples, the exponential function of complex variable. Okay, so let's see this. So just now exponential we know for a real number, so just like in real case how exponential is defined, e power x, it is defined as 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial, similarly till infinity. So this is how the exponential is defined in a real case. Okay, so similarly, this, if you have a doubt, you can just go back for the Taylor series and just expand e power x Taylor series. This is how it will come. Okay, so similarly we have exponential function for the complex variable z as x plus iy. Okay, so this is defined as e power z, which is exponential of z. This is written as 1 plus z by 1 factorial plus z square by 2 factorial, so on, the general term being zn by n factorial plus so on till infinity. This is how the exponential of a complex variable is defined. Okay, so now here we can actually, if you look at the exponential or exponential form of z, the exponential form of z is basically written as something like this. So this will prove why it is written as the exponential form is called as z will prove. Okay, so this comes from this definition actually. Okay, from this exponential definition it comes. So let's see. So e power z is 1 plus z by 1 factorial plus z square by 2 factorial, so on till infinity. So if I substitute, I mean z is x plus iy, so let x to be 0. Okay, so z becomes iy. So if I substitute like that, so e power iy will be 1 plus iy by 1 factorial plus iy whole square by 2 factorial, so on till infinity. So 1 plus iy, I square is y square by 2 factorial, so on you'll have, okay, infinity. So let me just let me just write down the third term also, z cube by 3 factorial, which will be iy whole cube by 3 factorial plus so on till infinity. So this iy whole cube will be I square into so it will be basically minus y cube by 3 factorial and so on. So this can be expressed in this form: 1 minus y square, all the real parts together will be something like this. Infinity. Similarly, all the I terms together, y minus y cube by 3 factorial plus y power 5 by 5 factorial. All this I can write. Okay. So now this, let us simplify it further. So if I simplify further, I can write cos y as 1 minus y square by 2 factorial plus y power 4 by 4 factorial, so on, is cos y. This is again from the Taylor series expansions of cos y and sin phi, and sin y can be written like this. Okay, so going by that, we can write iy as cos y plus I sin y. So in general, e power I theta becomes cos theta plus I sin theta. So this is a very important result. Now we know the polar form of z, which is z is equal to r cos theta plus I sin theta. This we have again seen from x plus iy, and writing x as r cos theta and y as r sin theta. So writing in that sense, it becomes like this. But now we have proved that cos theta plus I sin theta is e power I theta. So I can write z to be r e power I theta. So this is basically called as the exponential form of a complex number. Exponential form of a complex variable. Okay, so this is an important result. Okay, so we have seen the definition of exponential function, and then we have seen the important result e power I theta as cos theta plus I sin theta, and then the exponential form of a complex variable. So let's solve some problems. Separate into real and imaginary parts. Okay, so what they have given is exponential 5 plus I pi by 2. You need to separate. So this we can write e power 5 plus I pi by 2, which I can write e power 5 into e power I pi by 2. Okay, and e power 5 is e power 5. E power I theta is like cos theta plus I sin theta. So this can be written as e power 5 cos 90 is 0 plus I sin it is 1. So I can write I e power 5. So this has can be written as real. So real part is 0, imaginary part is e power 5. So this is how you can expand. So let's take another example. 5 plus 3i. We need to find out the real and the imaginary part. Okay, so this can be written as 5 plus 3i whole square. Okay, and let's expand this. So this becomes 5 square plus 3i whole square plus 2 into 5 into 3i. So this will be 25. I square is minus 9 plus this is 30i. So this I can write e power 16 plus 30i, and this going in the same form I can write e power 16 to e power 30i. So this is nothing but e power 16. Now expanding it using the exponential form, you can return cos 30 plus I sin 30. Okay, so the real part is e power 16 cos 30, and the imaginary part is e power 16 sin 30. The imaginary part which is attached to I. So basically all these things can be simplified. All the and anything and all the exponential of a complex number also can be expressed in just a plus ib form. Okay, real and imaginary form. So now let's see the circular functions of complex variable z. Okay, so circular means sine and cosine functions. Okay, of z. Now let's derive that. So e power I y, we know that it's cos y plus I sin y. Similarly, e power minus iy is cos minus y plus I sin minus y, which can be written as cos minus theta is cos theta and sin minus theta is minus sin theta. So this I can write. But now this is 1, this is 2. If you add 1 plus 2, you will get e power iy plus e power minus iy, okay, is equal to, we'll get 2 cos y. The imaginary parts will get cancelled. So from this I can write cos y as half of e power iy plus e power minus iy. Okay, similarly if I subtract 1 and 2, I'll get, if I subtract 1 and 2, so e power iy minus e power minus iy is equal to I sin y plus I sin y. So basically sin y will be 1 by 2i e power iy minus e power minus iy. Okay, so that's why, so in the same lines, I mean similar to this, I mean just going by the similar philosophy, sin z is sine of a complex number is defined as e power ij minus e power minus ij by 2 2i 2i. Okay, and cos z, the cosine of complex variable, is defined as e power ij plus e power minus ij by 2. So this is how sine and cosine of complex variables are defined. So now let's see the logarithmic function. Okay, so if z, which is x plus iy, and w, which is u plus iy, is related in this way, is related in such a way that, that exponential of z is exponential of w, sorry, exponential of w is z. Okay, so in that sense, then we call w is said to be logarithm of z to the base e, and is written as w as log z to the base e. This is how it is written. Okay, so also e power w plus uh, 2 and I n pi will be written as log. Okay, so let me just write down. So this is basically the definition. So if e power w is z, then w is log z to the base e. This is how the logarithmic of z is defined. Okay, so now if we have e power w plus I into y, I can just simplify it in this way. Okay, and e power w is z. Now e power it, this can be, we can use this way, cos theta plus I sin theta, important result which we derived. So you can write cos 2n pi plus I sin 2n pi. Now n is an integer here. Okay, so cos multiples of 2 pi, it's periodic in 2 pi. So cos 360 or cos 720 or multiples of that is basically 1 is equal to cos 0, and sin 0 or sin 360 or sin 720 is 0. So this is basically z. Okay, so e power w is z, and we know that e power w plus 2 I n pi is also z. So we can write log z is equal to log of w plus 2 I n pi. Okay, so logarithm of, basically logarithm of a complex number. I mean this is not log here. Okay, logarithm of z we can also write in this way, w plus uh, is w plus 2 I n pi. So logarithm of z, logarithm of a complex number has infinite number of values and is therefore a multi-valued function. Okay, because depending on n, it will have many values. Okay, so you can say that it's a multi-valued function. Okay, multi-valued function means if I give you a value of z, I can get so many values depending on n. Okay, if n is 0, it is only w, otherwise it can be w plus 2i pi or 2n pi. So all this happens because if e power w is z, then e power w plus I into 2n pi is also z. So based on that, the logarithm for function becomes a multi-valued function. So we have seen exponential function, we have seen circular functions sine and cosine, and we have seen logarithmic. Now let's see basic calculus of complex number, of complex numbers, complex function basically. Okay, so let's see the derivative, how it is defined, the derivative of f of z. Okay, so let's see how it is defined. So let w be a function of z, be a single valued function. Single valued means for every value of z you have only one value of w. Single value function of the variable z, which is nothing but x plus iy. Then the derivative of w is equal to f of z is defined to be dou w by dou z is defined as f dash z, and it is equal to the limit, and it is equal to the f of z plus delta z. So it is defined in a similar way how derivative is defined for a real number. Small change in z. So now this, the top numerator is the functional change in the value of z if there is a small change in z, such that the change vanishes to 0. This is how the derivative of is defined. So this is limit. Okay, LT is basically limit. Okay, now this is defined in such that provided the limit exists and has same values for all the different ways in which delta z approaches 0. So what it means is, first of all, a limit should be defined, limit should exist, then only you can call that dw by dz, or the derivative of w with respect to z, to be of this form. Okay, so in whatever way the delta z approaches 0, the limit should exist and should have the same values. So basically it means that the function should be continuous. Like in the case of real number, if a function is continuous, then only you can talk about differentiable. Okay, then only you can say the function is differentiable. Now when you say differentiable, you say it has a unique tangent. So similarly here, it means that if the limit value is same for all the values of, for all the limit value is same in whatever direction delta z approaches 0, then you can say that it has unique tangent, something like that. Okay, so now let's see an important theorem which basically talks about the necessary and sufficient condition for w to exist for all values of z. Okay, now okay, at one point, okay, derivatives define this. Now we are interested in what if the complex function of z, which is w, is defined for all the values. It exists for all the values. Means the derivative exists for all the values of z. So what is the condition for that? So let's see that. So what this theorem says is, we'll not prove this. We'll just lay down the statement. So necessary and sufficient condition for derivative of function w is equal to u of xy plus I v of xy is function of z to exist is basically is equal to f dash z. Okay, to exist for all values of z, to exist for all values of z in a region R. Okay. So these are the conditions. So if w is u plus iv and if it has to be equal to the derivative of z, that is f dash z, then what conditions w should, what are the necessary conditions for the derivative to exist at all points? That's the basic thing. So the condition is the dou u by dou x, the partial derivative of u with respect to x, partial derivative of u with respect to y. Similarly, the partial derivative of dou v by dou x, partial derivative of dou v by dou r. So dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou are continuous functions of x and y, are continuous functions of x and y in R. Okay, so that is first condition, and the second condition is that the derivatives has to be equal. I mean, the dou u by dou x has to be equal to dou v by dou y, and dou v by and dou u by dou y has to be equal to minus dou v by dou x. So these are the two important conditions. Dou u by dou x has to be equal to dou v by dou y, dou u by dou y has to be equal to minus dou v by dou x. So these are condition, and sometimes and most, I mean, in literature these are called as Cauchy-Riemann condition, Riemann condition, or basically typically called as CR conditions. Okay, so what are CR conditions? CR conditions has to be satisfied for derivative to exist at all points. Derivative to exist at all points. Okay, so for derivative to exist for all the points, okay, so let me not write let me write this as this as f of z only, it's not f z. Okay, so w is basically f of z. Okay, and w can also be written as u plus iv. Now for w, for the derivative of w to exist at all points, it should satisfy this Riemann condition. Okay, and also once it satisfies this, basically the partial derivative exists are continuous functions of x and y, and the CR conditions are satisfied, then one can write w dash, which is f dash z, as dou u by dou x plus I dou v by dou x, or dou v by dou y minus I dou u by dou y. So this is like differentiating with respect to x. Okay, I mean, you can forget about the y, you can just differentiate with respect to x, or you can just differentiate with respect to y and use this. Okay, so there are two important things here. For w, which is f of z, to possess derivative at all points, it has to satisfy these two conditions. Basically, the u and v should have the derivatives of u and v with respect to x and y should be continuous, and the partial derivatives of u with respect to x, dou u by dou x has to be dou v by dou y, and dou u by dou y has to be minus dou v. So it has to satisfy CR conditions, and once it satisfies, then you know that the the derivative w dash or f dash z can be just written in this way. It's like just differentiating with respect to x. Okay, okay. So this is all about the theorem. We will not prove this, but remember the statements are quite important. Okay, so now let's come to an important terminology: analytic function. Okay, so a function, see the definition. A function f of z is said to be, okay, uh, so when it is called analytic function, we'll see. So a function f of z which is single valued and possess a unique derivative with respect to z at all points of a region R, then that function is called analytic function of z in that region. It's called analytic function of z in that region. So a function f of z which is a single valued and it possesses a unique derivative with respect to z at all points. So this we have seen. What are the conditions for unit derivative? To possess a derivative at all points, we have seen the condition. Okay, the Cauchy-Riemann theorem. Okay, so this means that the analytic function should satisfy CR condition. Okay, so a point at which analytic function stops or ceases to possess a derivative, so that point is called singular. So when you say this function has become singular, it means that it is not derivative at that point. It doesn't have a derivative at that point. So the analytic function, going by the theorem which we have just seen, analytic function, for a function to be analytic, the CR equation, the Cauchy-Riemann equation, are nothing but the necessary and sufficient conditions. Necessary and sufficient condition for the function f of z to be analytic in R. To be analytic in R. Okay. So for a function to be analytic function, that is to possess a derivative at all points, it has to the necessary and sufficient conditions are CR equations or the Cauchy-Riemann equations. Okay, so now let's see some functions and let's see whether they are analytic or not. Okay, so check whether the function is analytic. Okay, if yes, find out the derivative. Find the derivative. So this is just applying that theorem whatever we have derived. So first example is w is equal to 2xy plus I into x square minus y square. Okay, so this I can always write u plus iv. So u is 2xy and v is x square minus y square. So now let's calculate dou u by dou x, which will be y. Dou u by dou y will be 2x. Dou u by dou x will be 2y. Similarly, dou v by dou x will be 2x and dou v by dou y will be minus 2y. So you can say that these are continuous functions in x and y. So condition 1 is satisfied. Condition 2 is dou u by dou x. So these are continuous. So condition number 1 is satisfied. Dou u by dou x has to be dou v by dou y. So let's see whether this is satisfied. Dou u by dou x is 2y and dou v by dou y is minus 2y. So these two are not equal. So it's not satisfied. Okay. Similarly, you can just look at the other thing. Anyhow, it's not satisfying, but still, if you want to look at the other thing, so dou u by dou y is 2x and dou v by dou x is minus 2. So 2x is equal to minus 2x, which is not possible. So CR conditions failed, Cauchy-Riemann condition failed, and the necessary and sufficient condition for function f of z to be analytic or basically W to be analytic. Okay, so has failed. So this is not analytic. Not analytic. Function is not analytic. Okay, so let's now see the other function, log z, log of complex variable. Let's see how whether it's analytic or not. So z, now in order to expand this, or to first we need to express in terms of x and y, right? So just to express in x y, let's use the exponential form. So this is what we need to check. Use the exponential form z as r e power I theta. So log z will become log r e power I theta, that is log r plus log e power I theta. So this is log r plus I theta, and theta, now r and theta can be written in x and y. So r is root over x square plus y square, theta as tan inverse y by x. Okay, so it is root over x square plus y square plus I theta, which is tan inverse y by x. Okay, so this root I can bring outside. I can write in this way, plus I tan inverse y by x. So this is like u plus iv. Okay, or u plus iv. I mean, let me write in this way, u plus iv. Okay, so u is half log x square plus y square, and v is tan inverse y by x. Okay, so dou u by dou x will be, let's differentiate, half log will be x square plus y square into 2x. It will be x by x square plus y square. This is a continuous function, except that x in, I mean, this is a continuous, yeah, this is a continuous function. Then similarly dou u by dou y is y by, similarly, I mean, because it's symmetric in x and y, so dou u by dou y will be y by x square plus y square. Now dou v by dou x will be 1 by 1 plus x square, because tan inverse x is 1 by 1 plus x square, and then the internal derivative with respect to x. So it is y is constant, and x 1 by x is minus x square. So this can be written like this, minus y by 1 simplified. Similarly, dou v by dou y is basically 1 by, so this is whole square, don't forget that, 1 plus y by x whole square. With respect to y, it is constant, so into 1 by x. So this will come out to be x by x square plus y square. Okay, so just check, let us check the condition. Dou u by dou x is dou v by dou y. That was the first condition. Let's see whether it satisfies. So y by x square plus y square and dou v by dou y is, I mean, dou u by dou y, actually, sorry, dou u by dou y. The first condition is basically dou u by dou y is dou v by, okay, so I mean, let's write down instead of just mentioning. So the CR conditions are dou u by dou x has to be dou v by dou y, okay, dou u by dou x has to be dou v by dou y, and dou u by dou y has to be minus dou v by dou x. Okay, so just check. Now dou u by dou x is basically equal to dou u by dou y, so condition 1 is satisfied, and dou u by dou y is equal to minus dou v by dou x, because if you multiply with minus, so these two will become equal. So together satisfied, both the conditions are satisfied. So you can say that CR condition is satisfied and the function is analytic. But only one thing is that at 0 comma 0 the derivatives will not exist. The partial derivatives will blow off. The partial derivatives blow off. Blow off means reach, are not defined. Okay, something like that. So except at that point it is analytic everywhere. So except at 0 comma 0 x comma y taking 0 comma 0, wz is analytic at all points, is analytic everywhere. Okay. Okay, so now if it is analytic, we are supposed to find out what is the derivative. dw by dz will be equal to dou u by dou x plus I dou v by dou x. Okay, so that will be basically x by x square plus y square, which we have just found out, and I into minus y by x square plus y square. So this comes out to be x minus iy by x square plus y square. Okay, and this I can actually write x plus iy, because the denominator I can always treat as x plus iy into x minus iy, and at the numerator I have x minus iy. So this can be written as x plus iy. Okay, and this is nothing but 1 by z. Okay, so I can say that log z is 1 by z. The derivative of log z is 1 by z, such that z is greater than 0. I mean, z is not equal to 0. Sorry, z can be negative, but z is not equal to 0. Okay, because otherwise this is not defined. So this is how a simple case to find out the derivative of function, but you have to check that first you have to check whether it is analytic or not. If it is analytic, then you can just differentiate by using this simple method. So we have seen what is a complex function. We have seen various complex functions like exponential, logarithm, and sine and cosine. And then we have seen what are CR conditions and why. There is a theorem saying that the CR conditions are the necessary and sufficient condition for a function to possess a derivative. And a function that possesses derivative at all the points is called analytic, and where it doesn't possess is called a singular point. Okay, now let's see a word about harmonic function. What is harmonic function? Okay, so we know that when f of z is u plus iv, okay, if it is an analytic function in some region of z plane, in some region of z plane, okay, so in some region of z plane, we know that if this is analytic function, then CR conditions are satisfied, right? So when CR conditions are satisfied, you can write dou u by dou x as dou v by dou y, and so this is 1. Similarly, dou u by dou y I can write minus dou v by dou x, so this is 2. Now if I differentiate 1 with respect to x and 2 with respect to y, okay, so then I can write dou square u by dou x square is equal to dou square v by dou x dou y. I can write 1, and the 2 will become dou square u by dou y square is equal to minus dou square v by dou x dou y, right? I mean, it will be basically dou y dou x, but we know that they are continuous, then you can always write dou square v by dou x dou y as dou square v by dou y dou x. Using this, the above equation will be basically dou square u by those two I can add, and it will be something like this: dou square u by x square plus dou square y by dou square by dou y square is 0. So this is basically called as the Laplacian of u. This is basically Laplacian equation, and u satisfied Laplacian equation. Similarly, if you differentiate 1 with respect to y and 2 with respect to x, then you can also prove that differentiating 1 with respect to y and 2 with respect to x, you can also prove that dou square u by dou and dou square v by dou x square plus dou square v by dou y square is equal to 0. So u and v satisfy Laplace equation. This is actually called Laplace equation. The operator, this operator is called Laplacian operator. Okay, okay. And this is the reason why they are called harmonic function. U and V are called harmonic function, and basically their theory is called potential theory. It's just a point where f of z is, if f of z happens to be a analytic function, then U and V are harmonic function. That is what, and U and V satisfy Laplace equation. So that is one point. Now point about another point is consider two families of curves. So u x comma y is c1 and v x comma y is c2. Okay, so two families of curve. Okay, so this is say 1 and this is say 2. Okay, so now if I differentiate 1 with respect to x, I can write dou u by dou x plus dou u by dou y, because y can be a function of x. So I can write dy by dx plus c is equal to 0. So this is just the differentiation of u, but y also can be a function of x. So dou u by dou x plus dou u by dou y and into the internal derivative. So dy by dx can be written as minus dou u by dou x by dou u by dou y, which can be written as, by the CR conditions, dou v by dou y and dou v by dou x. Okay, and let's say this is m1. Just say that this is m1. Okay, so similarly, I mean, this we have done on the equation 1. Similarly, if you do it on the equation 2, I can say that dy by dx is equal to minus dou v by dou x by dou v by dou y. This is taking equation 2. Taking equation 2, I got m2. Okay, so this now from here we can say that if you multiply these two, I mean m1 m2, it is minus 1, right? Just from both we can say that m1 m2 is minus 1. So what it means is that, I mean, if you just equate dou by dou x from here and here, you get that m1 is minus 1 by m2, or m1 m2 is equal to minus 1. So what we say is that they form an orthogonal system. So u and v basically form an orthogonal system. U and v form an orthogonal family of orthogonal system. Okay, u and v form orthogonal system or orthogonal. Okay, so if you have something like this, u, v will be something like this. So this is v and this is u. U is equal to some constant, v is equal to some constant. So u and v basically are orthogonal, because what we have seen is dy by dx. We have seen that the slopes, I mean, they are perpendicular. They are perpendicular, and the slopes, product of the slope is minus 1. So hence we can say that every analytic function defines two families of curves u and v which form an orthogonal system. So that is the point here, and we have also seen that u and v are harmonic. Okay, so a couple of points. What is analytic function, and then the properties of u and v. We have seen that they are harmonic and they form an orthogonal system. Okay, so we have not solved much problems, but we have solved two important problems. I mean, two practice problems, just to find out whether W is analytic or not. I think, and once it is analytic, you can just differentiate it with respect to x only, and the derivative of W with respect to h will be just like dou u by dou x plus I dou v by dou x. Okay, so this is about different.